So 8.3, we're going to work through some examples. Let's quickly mention our guidelines. So if we have an integral that has sine and cosine, not plus, but times, it could be that we have it could be that n is 0, could be n is any other integer. So if either sine is odd or cosine is odd, we're going to pull out one of the odd ones. And then, so for example, if we have sine cubed times cosine squared, the one that's odd is sine, so we're going to pull that odd one out, one of those, and that's going to leave us a sine squared. And then we still have our cosine squared. The one we pull out, that's going to be part of our du. So u is going to be the other function. So if du is cosine, u is going to be cosine, which of course we might have a negative in there or something as well. But the point is everything else is going to change to cosine. And we're going to be using sine squared plus cosine squared equals 1 to make that happen. So that's going to apply. If it's sine that's odd, we keep a sine with d theta, convert everything to cosines. If cosine is the odd one, we keep a cosine, change everything to sines. If they're both odd, it doesn't matter which one we take. On the other hand, if they're both even, if both are even, then we have to use an identity. Sine squared is 1 minus cosine 2x over 2, and cosine squared is 1 minus cosine 2x over 2. So if both sine and cosine are even, then we can't, if we pull one out, so that we have an odd here, then we would still be odd over here, and we can't use that identity with an odd amount of sines or an odd amount of cosines. So we're going to have to use this identity to rewrite that. So let's look at an example or two. Notice in this one we have an odd amount of sines. Now you might say we have an odd amount of cosines, but notice that's under the radical. So we're going to pull one of these sines to the end and make that part of our du. So we're going to have a sine phi theta out here. So u is going to be cosine phi theta. Du is going to be the derivative of that. The derivative of cosine is minus sine times the derivative of the inside function, and then d theta. So we're going to rewrite this. We're going to have our sine squared phi theta. We're going to have times the square root of cosine phi theta. We're going to have our sine phi theta d theta. And we need to pick up a negative 5. So multiply by negative 5, divide by negative here. And everything else has to be changed to cosines. This is already cosine. We need to change that to cosine. So if sine squared plus cosine squared is 1, that means sine squared is 1 minus cosine squared. So in this case, we have sine squared phi theta. So that's 1 minus cosine squared phi theta. This, we can change that to exponential form. Call that cosine to the 1/2 power. So we have a negative 1 in the front. This is what was sine squared. And we need to distribute. So do 1 times that. 1 phi theta to the 1/2. And then that, negative times positive is negative. Notice our bases are the same. This is cosine phi theta to a power. This is cosine phi theta to a power. So we add those exponents. to find out how many cosine 5 thetas we have. This exponent is 2, that one's 1/2, so 2 plus 1/2, 2.5, or 5/2. And then we have times -5 sine 5 theta d theta. So we multiply that together. We didn't put that on the inside of that because this is going to be du for both of them. That's our du. Sine 5 theta, so this is u to the 1/2. This is u to the 5/2. And then that's du. So to integrate that, -1/5 stays out front. This is going to be u to the 1 greater power over that power. U to the 1 greater power over that power plus c eventually. Now we just need to replace our u with what u actually is, which that's what? Cosine 5 theta. And then we can distribute, make the parentheses go away. So let's be careful. 2/3 goes on that one, 2/7 goes there. So we distribute, we have -2/15 cosine 5 theta to the 3/2, or we could put 3/2 there. Negative times negative, that's positive 2/35 cosine 5 theta to the 7/2. Let's see. So a little messy there, but the key is whichever one is odd, we're going to pull that to be part of our du, change everything else to the cofunction. All right, let's take a look at this one. This one doesn't have any cosines. The sign that it has is even, so we can't keep an odd amount of signs and change everything else to cosines. So here's where we have to use that identity that we mentioned, that sine squared is 1 minus cosine twice our angle over 2. So for us, sine squared of 4 theta would be 1 minus cosine of twice that angle over 2. Input. So if our input is 4 theta, twice that input is 8 theta. So that's what sine squared is. We want sine to the 4th. So how do you get sine to the 4th from sine squared? You square it. So that means we're going to have to square that. So sine to the 4th equals that numerator squared divided by the denominator squared. So if we square the numerator, that's 1 minus 2 cosine 8 theta plus cosine squared of 8 theta. Remember, when we square this or when we square this, we're not multiplying the insides together. Cosine 8 theta times cosine 8 theta, that's just cosine 8 theta squared, not cosine 64 theta. So we're not multiplying the angles there together. Same thing with the sine squared. If we're doing sine of 4 theta squared and we're squaring that, we have something with a power raised to a power, so we multiply the exponents together. We don't do anything with the input there. That's why that sine to the 4th, still 4 theta. That's why this is cosine squared, still 8 theta. So we can bring the 4 out front as 1/4. Integral angle of 1 minus 2 cosine of 8 theta plus cosine squared 8 theta. And then we have a d theta on the end. So we can integrate this. This is a constant. We can integrate that. That's just cosine. But here we have an even amount of cosines. So if we're going to amount of cosines, we have to rewrite using an identity. So let's do that. Cosine squared is 1 plus cosine 2x over 2. So whatever this angle is, that's our x. We're going to change that to 1 plus cosine of twice that angle. So 8 theta becomes 16 theta, and that becomes over 2. So 1 plus cosine of twice the angle over 2. Notice this is two terms. This is 1 over 2, and this is cosine 16 theta over 2. We can't divide 16 by 2. That 2 would have to come out front as a 1/2. But the reason I say this is when we combine like terms, we have a 1 right here. We're adding a 1/2 there. So 1 plus 1/2, that's 3/2. We have a 2 cosine 8 theta here. And then we have a 1/2 cosine 16 theta there. We just need to integrate each of those. So 1/4. When we integrate the constant, we pick up our variable. Minus 2 times, well, how do we integrate cosine 8 theta? We can handle the 2 however we want to. I'm just going to go ahead and write the 2 here. And then when we integrate cosine 8 theta, it's going to be 2 times whatever that answer is. So if this is u, then du would be 8 d theta. So we would need an 8 here and a 1 over 8 there. So that would make that cosine u, that would make that du. And remember what cosine integrates into, that integrates into sine. Sine of u. So when we integrate cosine of 8 theta, we get 1/8 sine of 8 theta. Then we have a plus 1/2 times whatever we get when we integrate that. So if we integrate cosine of 16 theta, d theta, that's our u. So du would need to be 16 d theta. So if I put a 16 there, we need a 1 over 16 there. So that's cosine of u, that's du. And again, cosine u integrates into sine of u. So cosine 16 theta becomes 1/16 times sine of u, where this time u is 16 theta. And then we have our plus c on the end. So we could distribute here if we wanted to, or we could pull out common factors, doesn't matter. Let's start here. 2 goes into 8 4 times. So we have each of these have a 2 on bottom. Here, this is 2 times 2, so we have a 2 on bottom here, and we have a 2 on bottom there. So we could pull a 1/2 out front. If we pull a 1/2 out front, if we pull that 2 on bottom out, we have a 3 theta there. If we pull that 2 out on bottom, we're left with a 1/2 sine 8 theta there. And if we pull that 2 out, we're left with a 1/16 sine 16 theta there. Can't reduce that 8 with that 2 because that's inside a function. Same thing here. That's inside a function. So that should be as far as we can go with that one. So we just have to be careful. We have to start out with what is our substitution going to be. Here, so we have to use our identity. Eventually we had to use this identity also. And then this one, it was just a basic integrate cosine u du. So if that's u, what would du need to be? If that's u, what would du need to be? Now the rules for secants and tangents are a little bit different. Remember that the derivative of tangent is secant squared. The derivative of secant is secant tangent. So the derivative of tangent is that. The derivative of secant is that. So if we have an even amount of secants, so if we have, for example, a secant to the 4th, we're going to keep an even amount of secants, and then we're going to take the other secants, and the secants that we're keeping, that's going to be part of our du, and we're going to change this to tangents. Why to tangents? If u is tangent, then the derivative of tangent is secant squared, so that would be du. So even amount of secants, we're going to keep an even amount, change the rest to tangents. And how do we do that? One is secant squared. So that's one thing. If the power of tangent is odd, so what if we have an, excuse me, an odd amount of tangents? So for example, tangent cubed times secant. Then we're going to pull one of these tangents over with a secant. That could be secant to the 1st, that could be secant to the squared or whatever. But we're going to keep, with that secant, we're going to keep the tangent. That's going to be our du. Once we take one of those tangents out, we're going to take the other tangents. We're going to change all of that stuff to secants. So if u is secant, then one tangent that we kept with a secant, that's going to be the derivative of that. It could be that we fall into both categories. It could be that we have an even amount of secants and we also have an odd amount of tangents. In that case, we just pick whichever one we like better. All right. There are a couple other ones. One of them says if we don't have any secants, if we just have tangents and have an even amount of, an even amount of tangents, then we're going to split this up. We're going to change one of these tangent squareds to 1 minus secant squared minus 1. And then we're going to multiply that out, see if we need to use any of the other rules. So let's look at, see what we have here. So here we have an even amount of secants. So we do have an odd amount of tangents, but let's go with the top rule first. If the top one works, we're going to do that. If the top one doesn't work, we're going to go to the next one. So the top one was, if we have an even amount of secants, what we do. So that's going to be part of our du. Secant pi x over 8 squared. So everything else we want to change to tangents. Well, we only had 2 secants, so we don't have any more secants to change to tangents. So all of these are tangents. That's going to be our u, tangent pi x over 8. So our du, when I said that's going to be du, that's going to be part of our du. We need to find out what else is going to go with that. So if we take the derivative of this, the derivative of tangent is secant squared times the derivative of the inside. Pi over 8 is a constant. The derivative of x is 1. And then we have our dx. So du includes a pi over 8 with that secant squared. The derivative of tangent is secant squared times the derivative of the inside. The derivative of that is pi over 8. So we have our secant squared. We need a pi over 8 there, which means we need to put 8 over pi on the outside. So 8 over pi, integral of u to the 23rd, and all of that is du. And we made that to be du. So to integrate that, that's just u to the 1 bigger power over that power plus c. So the 8 and the 24 reduce. So we get u, which is tangent. That's raised to the 24th power. And that's divided by 3 pi. So just what are we using for our substitution here? All right. Let's go to this one. So is our secant even? That's what we look for first. No, it is not even, so the first rule doesn't apply. Next rule, if our tangent is odd, so that means we're going to have a tangent on the end. So we're going to put those secants out. We're going to put that with our tangent. And all of that is going to be part of our du. And remember, what has a derivative of secant tangent? That's secant. So u is going to be secant. So what exactly is du going to be? It's the derivative of secant tangent, times the derivative of the inside function is 2, times dx. So we have our secant tangent. We need a 2 here and a 2 on bottom front. Secant, so u to the 4th, all of that is du. So that's just 1/2 u to the 1 greater power over that power. So that's u to the 5th. So secant 2x to the 5th over 10 plus c. So just knowing those rules. If you go into your book, that table is laid out for you. Just go top to bottom. If the top one doesn't apply, mark it out, go to the next one. If the next one doesn't apply, then go to the third one. So I think we may have one more. So what if we have 2 cosines or 2 sines that have different values on the inside? They're of different angles. Well, we have formulas to combine those. If we have cosine of ax times cosine of bx, to write that from a product to change it into a sum, that becomes 1/2 cosine of the angles subtracted. Let's see, that's a plus, yeah. And then plus cosine of the angles added. So 1/2 cosine add the angle or subtract the angles plus cosine add the angles. There are also ones for if they're both sine, and there's one if one of these sines and one of these is cosines. So again, those are formulas that would be in your book. So for ours, cosine of 7x times cosine of 9x, cosine of, in ours, the 7 is first, then the 9. But remember, multiplication doesn't matter. So let's take the bigger one, the smaller one. 9x, 7x, that's going to be 2x. Plus, add the angles. So 7x plus 9x. So 1/2, that goes in the front. And then we're just going to integrate cosine 2x, integrate cosine 16, and add those together. So just real quickly, if we're integrating cosine 2x, that's u. So du would need a 2 there and a 1/2 there. So we would have 1/2. The integral of cosine is sine. So we already have 1/2. And then when we integrate cosine 2x, we get another 1/2 sine. If we're integrating cosine of 16x, if that's u, then du needs a 16 there, so a 1 over 16 out there. And again, we're integrating cosine, so we get sine. So we can multiply this and then factor back out, or we can notice that has a 2, that has a 2, so we could factor out another 2 on the bottom to go with the 2 that we already have. And that'll give us the sine 2x and the sine 16x. So it's just a matter of using the identities to rewrite this into something that we know how to integrate. We try to integrate that directly. We have more than one cosine, so what's going to be u, what's going to be du. So we have to use an identity to rewrite that into something that each term has only one cosine. That we know how to integrate.